a geometric sequence. If you remember in 14.1, we were really just trying to understand what a geometric sequence is. And what we found is that a geometric sequence is really like a recursive routine. And we were even given that new rule, which if you look below is recursive rule. Given f of 1, f of n is equal to f of n minus 1 times r. And we made a bunch of formulas using the recursive rule, which was great. But as you know, it's a lot easier for us to find terms in a sequence if we can just plug in this specific number. So the recursive rule is really dependent on the previous term. So today we're also going to look at creating an explicit rule, which just allows me to, like, if I want to find the fifth term, plug in 5 and find out what the value of the sequence would be if n was equal to 5. Whereas the recursive rule, remember, I'd have to find f of 1, f of 2, f of 3, f of 4, and then I could find f of 5. So notice that the explicit rule is a little bit different. It has the first term in it, and then it's times that common ratio to the n minus 1 power. So basically, in order for us to create an explicit rule, we will always need the first term and the common ratio. So let's jump into an example. We're going to be looking at a little bit of a word problem. And we are going to ask to write a recursive rule and an explicit rule for each geometric sequence. So makers of Japanese swords in the 1400s repeatedly folded and hammered metal to form layers. The folding process increased the strength of the sword. The table shows how the number of layers depends on the number of folds. So if I look at the table, with 1 fold, it has 2 layers. With 2 folds, it has 4 layers. With 3 folds, it has 8 layers. And with 4 folds, it has 16 layers. So again, looking at my recursive rule, I can tell that my f of n's are doubling each time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So remember, to write the recursive rule, I really just need to say that f of n is equal to f of n minus 1 times the common ratio, 2. Okay? So that's the recursive rule. The explicit rule is a little different. Explicit rule, I need that first term. Remember, f of 1 times r to the n minus 1. So I know that the common ratio is still 2, but f of 1 is the first term, which is also 2. So I'm going to be 2 times common ratio is also 2, and this is to the n minus 1. So if I think about rules of exponents, then I can actually simplify this because it has a common base, 2 and 2. And so remember, I can think of this as 2 to the 1 power. And then combining, when I'm multiplying two numbers with the same base, I add their exponents. So it's to the 1 plus n minus 1. Notice that I have 1 plus n minus 1. Well, isn't 1 minus 1 0? So really, I'm just looking at 2 to the n power as my, probably simplify that. So 2 to the n power is actually going to be my explicit rules, which means if I just plug in a number, 2 to the first power, I get 2. 2 to the second power, I get 4. 2 to the third power, I get 8. This checks out. So my explicit rule is just 2 to the n. We're still looking at that same word problem for part B, but this time we're looking if there's 1 fold, then if there's 5 layers. 2 folds, there's 15. 3 layers, 45. 4 layers, 135, and 5 letters, 4 or 5. So again, remember, in order to write my rules, I need, for the first part, at least just to have the common ratio. And the common ratio in this case is 3 because 5 times 3 is 15. 15 times 3 is 45, etc., etc. So I'm multiplying by 3 each time. So f of n, to write the recursive rule, is going to be pretty simple. It's just equal to the previous term, f of n minus 1 times 3. And again, to write the explicit rule, I want to use the common ratio, but then I also want the first term, f of 1. Well, f of 1 in this case is 5. So for my explicit rule, I'm going to have 5 times the common ratio, which is 3, to the n minus 1. And again, this part right here, 5 and 3 are not like bases, so I'm not going to combine my exponents like I did up above in part A. So really my answer is just 5 times 3 to the n minus 1. Okay. Part C, we're looking at something a little bit different. Notice that now I'm not given my n values. I'm just given the f of n values. But because this is my first n value, I'm f of n value, I'm going to assume that's f of 1. So I have f of 1 is 6, f of 2 is 24, 96, 384, etc. So what am I increasing by each time? Well, every single time I'm multiplying by 4. So my common ratio is 4. 6 times 4 is 24. And you can check 4 times 24 is also going to be 96. So f of 1 is my first term, which is just 6. So if I'm writing my recursive rule, I don't need the first term. I'm just going to write f of n equals f of n minus 1 times common ratio is 4. And then again, the explicit rule is the first term. So 6 times the common ratio 4 to the n minus 1. See, this isn't too terrible, right? So hopefully you're really getting the pattern. And actually, just to kind of, for giggles in this, I'm just going to include f of n right here. Okay. Next, 4, 12, 36, 108, 304. Well, it looks like I'm multiplying by 3 each time. So again, common ratio is 3. And the first term is 4. So this is really pretty simple. So then if I'm writing my recursive sequence, f of n is equal to f of n minus 1 times 4. I'm sorry, times 3, common ratio, right? So that's pretty simple. And finally, the explicit rule. Remember, we like the explicit rule because I can find out any term without having to identify the previous terms. So explicit rule is really going to be your go-to. If you remember one of these formulas, remember the explicit rule. So f of n is going to equal to, remember, first term, which is 4, times the common ratio, which in this case is 3, to the n minus 1. And notice how we always have n minus 1 for our exponent. That makes it really simple. So hopefully now you can answer the essential question, how do you write a geometric sequence? If you have any questions, let me know. Not